Today, we want to review our Taylor series everyone should know, and then use them to come up with new series for things. Remember, we know we find Taylor series by matching derivatives, by creating a polynomial that matches the derivatives of the function that we're approximating. And also remember, we don't want to have to take all those derivatives. So we want to know how we can manipulate what we know to take care of the thing, to generate new things. So we should review the Taylor series that we should all know. E to the x is x to the n over n factorial. It's the one with all of them. Sine of x is the odd one. So it's all the odd powers, starting off with x and alternating sign. X cubed minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, and so on. And we're not surprised that there's a factorial in the denominator, which goes unchecked. So just like e to the x, this power series, the Taylor series for sine x converges for all real numbers. Remember that the interval of convergence, when a series converges for all real numbers, more terms means more accuracy. And more accuracy means our polynomial will be closer to the actual value, and it'll work on a wider interval. Any polynomial will have to go to infinity or negative infinity as x approaches infinity. So if we're trying to use this polynomial approximation for sine of x, and we're far away from 0, then we're going to need a lot of terms. We're going to need to use a lot of terms to really widen out the useful range for our model. But there are two aspects to making for the model being better. The values will be closer, and it'll work on a wider interval. So cosine x is the even one. It's also alternating, so I'll write minus 1 to the n. And it's the even power, so x to the 2n over 2n factorial. So it starts off with 1 and then alternates the even powers. Minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And just like sine, this converges for all real numbers. It would be weird otherwise. And we also talked about the binomial series, which was 1 plus x to the p. We didn't have a nice form for this, but we had a very nice pattern for this. So it starts off with 1 plus p times x. And then we just start writing the first n factors of p factorial, even if p factorial isn't going to be a thing because it's some weird irrational number. So we got p times p minus 1 over 2 factorial, x squared. Then for the cube, we write 3 factors of p factorial. So p times p minus 1 times p minus 2 over 3 factorial, x cubed. We know we can get some extra mileage out of these by just composing, making a composition of a Taylor series that we know. And sometimes we'll just plug things in to the Taylor series. So what this means is that if we want to approximate, if I want to approximate, say, the e squared, if I replace the x with a 2, this will be the sum as n goes from 0 to infinity of 2 to the n over n factorial. So that'll be 1 plus 2 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial, and so on. We know our approximation will get better the more terms that we use. 2 is, we might have to use a lot of terms initially because 2 is pretty far away from 0. But if we keep using, but since the power series, the Taylor series converges for all real numbers, we know that this will eventually converge to e squared. We can test that out. If we look at what e squared is 7.389. And if I start 1 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial plus 2 to the 4th over 4 factorial, we're at 7. So we need more terms. So if I add 2 to the 5th over 5 factorial, and if I add 2 to the 6th over 6 factorial, so go a lot faster if I just remembered my factorials, which I don't. We can see that even after only 6 terms, we're already at the nearest 10th. So let's watch how 2 to the 7th over 7 factorial. We're already at the nearest, we're almost to the nearest 100th. But we're only 7 terms in. Now we're at the nearest 100th, only 8 terms in. So the more terms we use, the better the approximation gets. If I wanted to use this approximation for a number, something further away from 0, I'm probably going to have to use more terms to get more accuracy. Any questions? All right. So this is one of the places where we find power series. We can create power series descriptions for functions, even strange transcendental functions like this. Now, we did one way we could build new functions is to just use a composition. So if I had a function that said e to the minus x squared, this is an interesting function because we know that e to the minus x squared does not have a nice antiderivative. That is, we can't express the antiderivative of e to the minus x squared with a finite combination of elementary functions, which means that we're going to have to negate one of those things, either an infinite combination of elementary functions or non-elementary functions. But with Taylor series, we can know this function really well. Actually, with our super 90s technology, we can know this function just as well. Well, we can approximate it by replacing the x in x to the n over n factorial with a minus x squared. So we'll have a 1 and then minus x squared. Minus x squared squared is going to be a plus x to the 4th. So plus x to the 4th over 2 factorial. Minus x squared to the 3rd will be a minus x to the 6th over 3 factorial. And so on. So we can see we're getting the alternating from this minus 1 to the n. And then it's going to be x to the 2n over n factorial. So here is an infinite combination of elementary functions. And we just find the antiderivative of this infinite combination of elementary functions for an antiderivative of e to the minus x squared. The other way, of course, is the second fundamental theorem. We can use a definite integral to construct an antiderivative for e to the minus x squared. So power series are useful for describing these functions. We can also use power series to construct solutions of differential equations. So before we begin down this road, we should note that this is not something that you should actually do, especially by hand, the way we're going to do it. So note that we're not doing this because this is something that you're going to have to know how to do in the future. But when a differential equation, we know, is an equation involving a function and its derivatives, and sometimes the independent variable. A differential equation is a description of a function. That's what we want, what we care about here. A differential equation is a description of a function. A differential equation is a description of a function. A Taylor series or Taylor polynomial is also a description of a function. So if we have a description of a function with a differential equation, we can create a description of the solution with a Taylor series. So let's see how that works. And as usual, we're going to do this on something that we're familiar with. So for example, let's consider the differential equation. Or the diff EQ, as the kids will refer to it. Let's consider the differential equation. Y is equal to, y prime is equal to 3 times y. So if you recognize the solution to this differential equation, that's because I'm picking one where we recognize the solution. But what we're doing is we're describing a function. We're describing a function such that when you take the derivative, you just get 3 times what you started with. A differential equation is a description of a function, just like any equation is a description of a number. When I say 2x minus 5 equals 13, that's a description of the number x. And we can use that information to figure out what x is. Similarly, here's an equation involving a function y and its derivatives y prime. It's just a description of the function y. So notice that this is a description of the function y. That differential equation is a description of the function y. Let's pretend that we don't know that the solution is some constant times e to the 3x. We're going to play pretend here. Let's suppose we don't know the solution. We're going to suppose that we don't know that the solution is y equals 3e to c, some constant c times e to the 3x. And let's assume that there's some power series solution. Burrell's theorem gives us that every power series is a Taylor series of some smooth function. So let's try to use that. Let's guess at a power series solution. We're going to guess that y is equal to the sum as n goes from 0 to infinity of c n x to the n. I'm going to guess that this is what the solution is. That is, this is my guess for a solution to the system. Y equals c0 plus c1 times x plus c2 times x squared plus c3 times x cubed and c4 times x to the fourth, and so on. I'm going to guess that this is our solution. The solution's form is determined by power series. We're just saying there's a power series solution. The specific power series will be determined by these coefficients. So I need to figure out what these coefficients are. What do these coefficients need to be to fit this description, y prime equals 3y, 3 to the y, excuse me. So we're thinking now, what do these coefficients need to be? To satisfy the differential equation. What do these coefficients need to be to satisfy the differential equation? So this is just a guess, and we're using the tried and true method of just guess and check. When in doubt, guess. So if y is c0 plus c1x, that's going to go in for, sorry, if y is c0 plus c1x, c2x squared, that's the sum c and x to the n. That's going to go in for the y. I also need something to go in for y prime. So y prime, c0 drops out, and I just get c1 plus c2 x to the first plus c3 x squared plus c4 x cubed. I forgot stuff. Suddenly forgot how to take derivatives. Y prime is going to be c1 times x to the 0 plus 2 c2 x to the first plus 3c3 x squared plus 4c4 x cubed, and so on. I could write this in a compact form by taking the sum of n times cn x to the n minus 1. That is, just take the derivative of the terms that we started with. Makes sense. We can do this a term at a time. Note that our counting here, I want my first term to be an x to the first. So my counting starts at the n will start off at 1. So let's see, 1c1 x to the 0. So I dropped off that first term. Now, let's just plug this into the equation. I've got an expression for y, and I've got an expression for y prime. Let's put those into the equation. So I've got y prime Let's substitute y and y prime into the differential equation. So I got y prime is c1 plus 2c2 x to the first plus 3c3 x squared plus 4c4 x to the third, and so on. And on the other side, this equals 3 times y. And y is just c0 plus c1x plus c2x squared plus c3x cubed, and so on. Now, if these two sides are going to be equal, that means the coefficients have to be the same. So we're going to equate coefficients. And we're going to equate the coefficients of the powers of x. So the constant on the left is c1. The constant on the right is 3c0. So that means that c1 has to equal 3 times c0. c1 just equals 3c0. The coefficients of x must also be equal. So c2 is equal to the coefficient of x on the right, which is 3c1. Oops, sorry, 2c2. I forgot I wanted to write the whole thing. 2c2, the coefficient of x on the left, is equal to the coefficient of x on the right, 3c1 times x. Or sorry, just 3c1. The coefficient of x squared on the left is 3c3. And the coefficient of x on the right is, x squared on the right is 3c2. The coefficient of x cubed on the left is 4c4. And the coefficient of x cubed on the right is 3c3. Now, and this would keep going. If we needed more, we can keep going. What we can do now is write all the coefficients in terms of just c0. Since c1 is 3c0, that c1 is in terms of 3, 0. So here we have c1. Here's c1 in terms of c0. C2, 2c2 is 3c1, so I can solve for c2. So this tells us that c2 is 3 over 2 times c1. But c1 is 3 times c0. So c2 is 3 halves times 3c0. So it's going to be 3 squared over 2 c0. Now I've written c2 in terms of C0 as well. In C3, we can solve for C3. C3 is going to be 3 over 3 times C2. But we have C2 in terms of C0. So C3 is going to be 3 over 3 times 3 squared over 2. Oops, C0. So I'm going to get 3 cubed over 3 times 2. Now we have C3 in terms of C0. And we'll just continue on. You can see that we can do this forever. And you can notice that also that I'm not simplifying things. In this case, it doesn't actually help to simplify things because we want to see the structure of how things are built. So let's solve for C4. C4 is just going to be 3/4 C3, but we have C3 in terms of C0. So C4 is going to be 3/4 times 3 cubed over 3 factorial C0. So that's going to be 3 to the 4th over 4 factorial times C0. And so now we can see what Cn is going to be. We can see that Cn is going to be 3 to the n over n factorial times C0. So now we can see that Cn is going to be 3 to the n over n factorial times C0. And now we recognize 3 to the n over n factorial as the coefficient of e to the third. Any questions? This is not something that we want to do by hand, but I'm just trying to illustrate the point that we can use a power series as a guess for a solution to a differential equation. Clearly, we would want a machine to do this depending on how complicated our differential equation is going to be. But based on this, our solution looks like the sum as n goes from 0 to infinity of 3 to the n over n factorial times C0. Oops, 3 to the n times x to the n. And so we can recognize this as C0 e to the third, to the 3x. This is something that we already knew. That's the point of testing things out. The first test for some new process should be on something that we know should work. Then we can try using it on things that we think will work. All right. One of the reasons that I wanted to do this is that a lot of times in math, we're asked to solve equations, and then we learn some technique for solving an equation. Like we learn the completing the square technique, or the trash version of completing the square. We learn the quadratic formula. So a lot of times we learn some technique, and it starts to build the idea that there's a technique for every equation, and this is just not true. There are equations that there's no algebraic technique that will lead us to an exact solution. Sometimes all we can do is guess, and then check, and then refine. But guess, check, refine is pretty much how science works. So we need to get used to that idea. An analogy that I think is apt is that when we learn to factor polynomials. So set your Wayback Machine to algebra when you were factoring polynomials. And because your teacher wanted you to learn how to factor polynomials for some weird, mysterious reason, you factor a bunch of factorable polynomials. They hand you a big stack of factorable polynomials and say, factor these. And very few of them are prime polynomials because they want you to practice factoring. The problem with that is that it creates this bias in our mind. We start thinking that most polynomials are factorable. And it's just focused on your experiences, which is a bias that a lot of people are equipped with. In my experience, as an algebra student, most of the polynomials that we encounter are factorable because most of the polynomials you've encountered are factorable polynomials. But you ignore the parts where you have been handed this weird biased set of polynomials, most of which were factorable because we wanted you to practice factoring. So I guess you just always need to examine why you think the things you need to think. Same thing happens when we start learning all these weird techniques. And from the way that I think of algebra is that we have one grand technique for solving equations. Perform inverse operations in reverse order. That's how we solve equations. Things like solving radical equations by squaring both sides, that's just variations on that one technique. And so we learn all these techniques for solving equations where the variable appears a whole bunch of times. We learn to solve radical equations where the variable appears multiple times. We learn to solve rational equations where a bunch of denominators have variables in different forms. We learn to solve quadratic equations. And we learn to solve cubic equations. I'm just kidding. None of you learned how to solve cubic equations because apparently that's where we'll draw the line. It's because we can get away with the quadratic formula, if you're wondering about that. And the cubic formula is much more complicated. So we get this skewed idea that there's some technique that we can use to solve the equation. But there are equations that we can write down that just don't have a technique that will lead us to the correct answer, to the exact answer. So the best we can do is approximate it. We grab a machine and say, hey, machine, how close can you get me to the solution of this equation? And this machine says 12 decimal places. And that's good enough for almost every application we could possibly think of. 12 decimal places is pretty awesome for a machine from the 90s that you can carry around in your backpack. And then your phones come along and say, hey, we can do way more than 12 decimal places. And we're like, well, hey, iPhone, stop being so extra. You also cost 10 times as much as a calculator. And iPhone's like, oh, yeah, I forgot about that. You know what I mean? Oh, hang on. Do you have a question?
Yeah, I was going to ask about the second to last step where you have 3/2 multiplied by C, or I'm sorry, 3 times C0.
Uh-huh.
Can you explain how you got that again? I got lost there.
From here, 3 squared over 2. That's
yeah, leftover. Yep, exactly.
Yeah, so we've got C1, or C2 is equal to 3 squared over 2 times C0. And I just took 3 squared over 2 times C0 and replaced the C2 when I was trying to solve for C3.
Oh, so the same thing for C1, C2, C3 is you just replace those with.
Yep. C2 was
Oh, I
3
see.
squared over 2, C0. C3 is 3 cubed over 3 factorial, C0, and I just put that in.
Got it. Thank you.
I want to write everything in the lowest C that I can find.
Okay, thank you.
Everything could be in terms of C0 here because my biggest derivative was y prime. So I only had that one constant. If I started off with an equation of y double prime, then I would have had everything in terms of C0 and C1. If you're interested in practicing this technique, which I said you should never do by hand, which I said you should never do, you should also, you can try, say, y double prime equals 9y. This is an equation that we can solve by inspection. If y double prime is equal to 9y, we know the solutions are going to be either something times sine of 3x or something times cosine of 3x. Because the second derivative is just going to be a constant times what we started with. Oh, whoops, -9. Yikes. Because if we start off with sine of 3x, the derivative is cosine, 3 cosine of 3x, and the derivative of 3 cosine 3x is -9 sine of 3x. That's -9, what we started with. So take two derivatives of our guess at what y should look like, plug them into this differential equation, and then start sorting out what the coefficients need to be. Since we know that there are two solutions to y double prime is equal to -9y, sine and cosine, sine of 3x and cosine of 3x, we're going to write a bunch of stuff in terms of C0 and a bunch of stuff in terms of C1. The C0 ones look like they're going to be the cosine because that's where the evens, and the C1s are going to be the sine. All right, that would be a fun activity to do. Try to solve y double prime is equal to -9y using a power series solution, a Taylor series near zero. All right, so that's going to do it for today. Maybe I have a weird definition of fun, but that would be fun. That's going to be it for today. I will see you all on tomorrow. Everybody have a good day. Do your two new quizzes, quiz 11 and quiz 12, and thanks for playing.